No other logic circuit displays this property or characteristics. The property is called mirror property. That means, let's say in a full adder circuit you send AB two inputs and a carry in. It will produce a carry out and a sum bit under normal circumstances. So according to the mirror principle, if you invert A, B and C, that means instead of A, B and carry in, if you apply A bar, B bar, C in bar, carry will be inverted, sum will be inverted. So that is unique property. That means if you send two inputs and the carry in through an inverter, this bubble means inverter, through an inverter signal, your sum and carry output will also be in inverted form. If you were expecting a 1 here, it will be 0. You are expecting a 0 here, it will be 1. Inverted form. That is called mirror technique. That means if we invert sum of ABC, the result which is equal to sum of A bar, B bar, C bar. Same thing with carry. So using this observation, unique property called mirror property, they can implement an adder circuit with much simpler design, and that is called mirror adder design. So mirror adder design is it's very simple. This is the CMOS side, the pull down side of a full bit mirror adder circuit. If you know what is the mirror, the NMOS side or pull down side, then in regular CMOS circuit, what you will do? You will convert the series connection to parallel connection to series. But due to this mirror property, it gives us a unique way of implementing the CMOS circuit for full adder. So this is the pull down network, pull up network will be a mirror image of pull down network. That's why it's called mirror technique.
Okay.
It comes from that observation in the previous slide. Its pull up circuit will be a mirror image of the pull down circuit, only the transistor will change. That means series will remain series, parallel will remain parallel, and the transistors connections will remain exactly same, but NMOS will become PMOS. So as you can see, this is the complete mirror circuit of a full bit adder, 1 bit full adder. This is my pull down network, this is my pull up network. So using this mirror technique, so it is much simpler. It reduces the number of transistors, but it has one problem. As we increase the number of input bits, we will have some long series chain of transistor appearing in the circuit.
But
so this is, yes.
But it is good.
Yeah,
it is
much
better than the before the adder.
It is an improvement. It is an improvement, but it's still in every designer implement, they try to look at what is the bottleneck, how can we improve it further, right? So this one is a complete mirror adder circuit for a full adder circuit, both the NMOS side and the PMOS side, with both sum bit and the sum bit and the carry bit generating circuitry together, complete implementation, and it needs 24 transistors. So further reduction was simpler, but the problem is appearance of this long series chain of transistor. So we started with 36, came down to 28 transistor. With mirror technique, we came down to 24 transistor with one problem, that long series chain of transistor in some case. And we can also implement the same adder circuit, sum bit and carry bit, using transmission gate based multiplexer, and transmission gate based multiplexer that also is much simpler design. You have 1, 2, 3, 4 transistor. You have 1, 2, 3, 4, 5, 6 transmission gate. 6 means 12 transistor, right? 6 transmission gate means 12 transistor, each of them 2. So 12 plus 4, 16 plus 2, 18 transistor, right? So it is much more improvement. So you don't need to go through the details of all these adder circuit design. I'm just showing you different alternative circuit design proposed by different design group. Yes.
The first adder that you have explained, but we need to for the exam we need to understand that if anything question
no,
comes.
Everyone just go through the logic to see how this one is actually implementing the logic for the carry out. This one is implementing logic for the sum. To understand the operation of the circuit, try to relate it with the actual logic equation. Let's say randomly put a 1 and 0 here or 0, 1 here and assume a carry in, and then try to see whether it is producing the right result, so that you understand the operation of the each of the circuit. So this is in computer engineering, coming up with different design for better adder circuit or optimizing adder circuit design. It's an ongoing research. They're always looking for better adder. So the original equation we proposed, we introduced, that actually the direct representation of the way we do hand calculation. So that first logic equation came from the way we do the hand calculation in full adder, and then that led to a 36 transistor implementation. So now we are showing different logic level and circuit level improvement to basically improve the design and minimize the number of transistors per adder bit. The next one is called Manchester carry chain adder circuit design. This one utilizes the intermediate signals we have introduced. We have introduced 3 intermediate signals: delete or kill, propagate, and generate. Based on the input variables, A's and B's, we can predetermine whether there will be no carry, 0 carry, whether the same carry in will be the carry out, whether there will be new carry 1, irrespective of what are the carry in, right? So that decision we can make preemptively just by looking at the input combination. So we introduce these 3 intermediate variables: delete, kill, propagate, and generate. So Manchester carry chain circuit design, adder circuit design technique utilizes these 3 intermediate variables. These are the relation. Carry out can be expressed in terms of generate and propagate and carry in. First initial carry in, which is always 0. Sum bit can be expressed as a function of propagate and carry in. As I mentioned, in some literature, this one will be called kill. In some literature, this one will be called delete. So the symbol will be the D or K. So the book from where I took this particular example from, it uses kill, not delete, same thing. So here, from that bigger truth table, I just wrote the value of propagate, generate, and kill or delete signal for all possible input combination for a 2-bit adder. For 0, 0, kill will be 0, kill will be 1 for 0, 1, propagate will be 1 for 1, 0, and also propagate will be 1 for 1, 1, generate will be 1. So from that truth table, we can build a very simple circuit. Of course, we need some extra logic gate to produce the signal P, generate and kill. Because we need an AND gate to generate this one, OR gate to generate this one, so XOR gate and an AND gate to generate kill, right? And 2 inverter here. So that is a one-time expenditure. For repeated calculation, what we can do, we can come up with a simple circuit using this equation we introduced in that slide. So, as I mentioned earlier, for adder circuit, it is the carry generation that is the most critical, because carry has to travel through entire chain of the adder. Some bits are already available by the time you get the carry. So, utmost emphasis is given to improve the carry. So, we are showing the carry circuit here. So, carry out, if propagate is 1, what that means that carry in and carry out will be the same. So, I put an NMOS transistor between carry in and next carry out with an NMOS transistor. If propagate is 1, this transistor is on, I can send carry in directly to the carry out without even thinking what happens to the adder, right? Because it's propagate. If kill or delete is 1, that means this carry will be 0 no matter what happens in the adder. So I put an adder, a transistor with controlled by kill or delete signal and connecting it to the
0.
So if kill is 1, this one is connected to ground,
No.
so it will get a carry out. Next adder can start its operation without this adder to finish its job. And when the generate is 1, that means we will always have a carry out equal to 1. So I put another transistor here, controlled by generate signal, it is connected to VDD. So these 3 transistors can make the decision for the next adder, and next adder. So after every adder, we will put these 3 transistors, so we can actually expedite the operation significantly. So you can say that, well, NMOS transistor, if you are propagating a 1, this case and this case, probably there will be a distortion because NMOS is not very good at propagating 1. So we can use a transmission gate here, we can use a transmission gate here, right? If we want to get a strong signal like this one, right? Or this one. Or in case of NMOS, we can invert it and put a PMOS transistor here, right?
Yeah.
We can invert this generate and put a transistor here, so it will give a full strength VDD here. This one we don't have to worry because NMOS can pull it down all the way to 0. It can deliver a perfect 0. Now this is the regular 2 alternative static implementation of carry generation circuitry using Manchester carry chain adder technique. We can also make it a dynamic. Wow! Between generate transistor and ground, if we put a clock, between here and VDD, if we put a clock control, then sometime if clock is off, this node will be floating, it will be maintaining its value across a parasitic capacitance, and that becomes the dynamic implementation. So same circuit we can implement using dynamic technique. So this is called Manchester carry chain. So now if you want to implement a multi-bit adder circuit using this one.
Question. Real
Yes.
quick. Just going back. So on A, so that transmission gate is being used to strengthen the ability for
Yeah.
it to propagate 1
Yeah.
on A.
So this is, I'm replacing this NMOS transistor
Yep.
with this transmission gate. That's why I draw it side by side.
And it allows you to propagate 1 better
Yeah.
in that
Yeah.
condition. And then they add in PMOS to the VDD side again to
Same thing, because
Same thing.
PMOS is very good pull-up, because
Right.
if generate is 1, this will try to set this to 1, but this NMOS will impose a threshold voltage drop, like NMOS is not very good at passing 1, so that's why we use PMOS. But if we use PMOS to turn it on, instead of generate, I have to use generate invert.
I can't tell on that side, is that kill and the generate, are they also inverted on both of these? Or is
No.
it just inverted on this
No.
delete?
Because these are taken, so K and D plus So K, if K is 1, this NMOS is on.
Yep.
So this node can go all the way down to 0 because NMOS is very pull down.
Yep.
That's why in any of these three options, I'm not changing this NMOS transistor.
Okay,
Because
so
there
that's
is
not
there is
okay.
connected to the ground.
Gotcha.
NMOS is very good at pulling down.
Cool.
Yeah. We are only touching this one because sometimes we have to propagate 1, sometimes we have to propagate 0.
Gotcha. Yep.
Yeah. And this one will be always transferring 1 here.
So I have a question.
Yes.
P in the first one we have PI only NMOS, but there is NMOS and
Because it's a
PMOS.
transmission gate. In a transmission gate
Okay.
is if you remember, transmission gate is a parallel connection.
Oh, yeah.
NMOS and PMOS. Yeah.
Got it. So it can pass 1 and 0
Yeah,
at the same
1
time.
and 0 without any distortion.
Okay.
So this is the implementation of a full bit, 4-bit adder circuit carry out circuitry. So if this propagate is 1, this carry can go here. This propagate is 1, this carry can go here before this can finish its job. If this propagate 1, this will go here. If this propagate 1, go here. So if all 4 propagate signals are 1, this carry can be copied all the way here to generate the final carry. But it is very unlikely that all 4 propagate will be 1, that you will have that type of input combination. But in this chain of 4 propagate transistor, if half of them are 1, then you can save half of the time. Half of those adder arrays can start their job parallelly. So, and if you make it a 6-bit, then you have to add 2 more columns, 8-bit, 2 more columns. So this series chain will increase. So this is the carry generation circuit for a 4-bit adder, and as you can see, it is much simpler. The entire 4-bit adder can be implemented, the carry generation circuit can be implemented with just a bunch of transistor and some inverter. So it is a much simpler design, but only problem is this, again, this series chain. We are talking about a 16-bit transistor, in this adder, there will be 16 transistor in series for 16 propagate signal. So every design has some advantage, simpler implementation of the circuit, but it will have some its own disadvantage. So now, up until now, all the techniques we are showing is logic level manipulation or circuit improvement. But these are focused on improving each individual full adder circuit. Up until that Manchester carry chain, we are talking about how can we improve one full bit adder to add 2 input bits and 1 carry in bit to generate a sum and carry out. How can we improve 1 bit full adder circuit, right? But in a real computer architecture, we are talking about 8-bit, 16-bit, 32-bit, 56-bit, 128-bit, 256-bit, right? So you have a very large array of adders. So in actual adder circuit, there will be many full adder circuits that has to be implemented as a bank of adder, which will be most likely equivalent to the size of the bus or size of the word, because you will be taking one word at a time. So if the word size is 64-bit, so you have to be able to add that 64-bit with another 64-bit number at the same time. So your corresponding full complete adder array must have 64 full adder, right? Because one full adder can handle only one pair of bits. So now we are looking at architecture level, overall adder architecture level manipulation. Now we have seen different circuit level implementation, what goes into this rectangular box. Now at the architecture level, we already implemented the simplest one. The simplest multi-bit adder architecture will be the ripple carry adder. We just add them in series from right to left, the way we do the hand calculation. So the adder will have a delay equivalent to n minus 1 times t carry plus 1 t sum, which we explained earlier. But as you can see, here the delay will be order of n. Let's say t sum and t carry, they're equal. Time to generate one sum bit and time to generate one carry bit is equal. Then it will be the order of n. So for 64 bit, your delay will be 64 times the delay of one adder, right? So it is a very inefficient design. So, but as I said, your entire computation is dependent on adder operation. Everything else in the computer is auxiliary device. Your adder is the main computational core. Your CPU is the computational core. Inside the CPU, data path where a computation will take place, and inside the data path, it is the adder circuits which will be performing all the computation. Everything else inside the CPU and outside the CPU are considered as auxiliary supporting element. So if your adder waits for, if the adder delay increases of the order of number of bits, then system becomes very slow. That's why even if you have to add lots of redundancy in the adder array, you have to do it to improve the overall performance. So now let us see what architecture level improvement we can adopt to improve the delay of a regular ripple carry adder. One of them is called carry look ahead adder, that we look at the carry ahead of time using those intermediate signals, propagate, generate, kill, and then we basically send the carry preemptively to the next block so that next block can start its operation. So this implementation will basically based on getting the input signal first, calculating all the propagates and generates and kills and deletes in one step, and utilize those intermediate signal to basically predict the carry ahead of time and do as many addition operation in parallel as possible. You cannot do everything in parallel, but you can do many addition out of those 64 bit in parallel. So that is the principle of carry look ahead adder. Carry look ahead adder is based on these two equations. Remember, carry out or carry in for I plus 1 column is equal to generate of ith column plus carry in of ith column times propagate of ith column. And sum bit is an XOR of propagate of ith column and carry in of ith column. Using this equation, carry look ahead adder can actually generate all the carry signals for every column in one step. That saves tremendous amount of time, but the expense of complex circuitry to generate all the generate, propagate and kill signal in one time, that circuit will become very complex. As we increase the number of bits, we will show it a little bit later. So now, this is general expression of carry out and sum bit in terms of generate and propagate signal. Now if let us assume a 4-bit example. So for a 4-bit examples, it will be C1, C2, C3, C4. Carry out 1, carry out 2, carry out 3 and carry out 4. Initial carry will be C0, right? Initial carry will be C0. Then it will go to first column, second column, third column. The output that will be 0th column, first column, second column, third column. The carry out of the third column will be C4. Carry in of the 0th column will be C0, right? So C1 will be generate 0 plus carry 0 times propagate 0. C2 will be generate 1, C1, P1. C3 will be G2, C2, P2, right? so on. If I have a C5, then I have to. So now as you can see, C0, by default we know that it is 0. Because when we start adding from the rightmost column, whether it's a decimal addition or binary addition, when we start adding from the rightmost column, which is called 0th column, there is no carry in. That is by default 0, right? So we already know it is by default 0. So this term is gone. The input for that 0th column, rightmost column, we know. From that we can calculate, generate, so we can calculate its carry out, right? If we know its carry out, now C1 is embedded inside C2. The moment we know this value, the moment we know this value, so we also know this value. Why? Because generate 1 and propagate 1 can be calculated from the inputs, you already know that. As soon as you get C1, simultaneously you can calculate C2. The moment you know C2, simultaneously you can calculate C3, simultaneously you can calculate C4 because C3 is embedded inside C4. So now, let's start replacing everything to express everything in terms of known value. C1 is already expressed in terms of known value. Generate 0, propagate 0 we know from the input. Carry 0 we know is by default 0. So now inside C2, let's put value of C1. So now in this expression of C2, we know generate 1, we know propagate 1, generate 0, propagate 0, propagate 1, and C0 we already know. So now I have expressed C2 in terms of all the known value right after the first step. In first step, we calculate all the generates and propagates for every column. C3 similarly is expressed in terms of all the known values we know or we calculated in the first step. C4 also, we can keep adding. C5, C6, all the way up to C256, right? If it's a 256-bit adder. So that means all of the carries are expressed by known values utilizing those intermediate signals. So now if we want to implement this circuit, this logic expression into actual circuit, how it looks like. This is the implementation of the 4-bit carry look ahead, but as you can see, successively the circuit is becoming complex and the number of inputs for each of those logic gate is increasing from 2 to 3 to 4 to 5. It is increasing. So we have to watch out for that. Now once we know all the carry for a 4-bit adder, all 4 carry out, if we know from this expression sum is of an ith column is an XOR of propagate of ith column and carry of ith column. So what we can do, once we know all the carry, we already know all the propagate, use just 4 XOR gate to get all the sum bit. So in step 1, we are calculating all the propagates and generates. In step 2, we are calculating all the carry. In step 3, all the sum bits are already there. So you have the final result after step 3. Of course, step 2, generation of the carry, that has 2 layers. First layer, we have lots of logic gates with many inputs. It may make it a little bit slower. It will be clear why it is slower in the next slide. But in 3 or 4 step, you are done with all the result irrespective of how many bits. Successive bits will become a little bit more complex and slower, but overall it is better than order of n. N is the number of bits. If you have 256 bit, it will be order of 256, the delay. Here, It's a 4-step process. Step 1, propagates, generates, and calculated. Step 2, carries are generated. It's a 2-step logic process. Step 3 and 4, you calculate the sum bit. So maximum 4 step, you have the result instead of order of n. Now, why increase carry look ahead adder becomes slower if the number of bit increases? Because if I have to have a C5, then I will have 5 gate in the layer 1 and then another gate in the layer 2, right? So it will increase. It will be evident when we draw the actual CMOS circuit. So this one, the CMOS implementation of carry 1 logic. Carry 1 logic is what? G0 is in OR operation with this AND operation. Between them, they will be in series. Together, they will be in parallel with this one. If we implement it in CMOS, will we get C1 or C1 bar? C1 bar. So if you look at the CMOS implemented, I'm just showing the NMOS side of the circuit. NMOS side of the circuit, as you can see, C1 bar is Z0 in parallel to P0, C0, right? Now, look at the equation. This C1 is embedded inside C2. C1 will be in series with P1, right? So now, if you look at the second circuit, this is my C1 is in series with P1. The whole thing will be parallel to G1 and result will be C2 bar. The whole C2 is embedded inside C3. So this is my whole C2, which will be in series with P2. The whole thing will be parallel to G2 to C3. The whole C3 is embedded inside C4, right? So now, as you can see, with the number of bits, this series chain is increasing. So there is one bottleneck in carry look ahead adder. With the increasing number of bit size in your adder circuit, you have a long series chain of the transistor.
Parasitic will increase.
That will slow down. If your signal needs to pass, if all the propagate signals are 1, then you have to travel from here to here to here to here. That particular path will be extremely slow. It will slow down the whole system because every computation depends on this. Now so this is one serious bottleneck. That's why carry look ahead adder is good for smaller adder arrays. If it goes beyond 8 bit or 16 bit, even beyond 8 bit, it becomes very slow. Once let's say it's a 4 bit. Once you build the NMOS circuit, now if you want to implement it as a regular CMOS, you just generate a regular PMOS circuit here in this block. This will come here in this rectangle. This regular PMOS circuit will be series will become parallel, parallel will become series. But if you use mirror technique, PMOS will be the mirror image of NMOS. Series remains series, parallel remains parallel as it is, only the transistor will change. Or you can plug that NMOS network into, remember the pseudo NMOS logic. You can plug them into a pseudo NMOS logic, becomes a pseudo NMOS carry look ahead adder, or you can use to clock signal, you can make it N-type dynamic implementation of full adder. You see that we are repeating everything we learned from before, the basic techniques, different types of CMOS implementation.
That's a pseudo NMOS, and
that's a pseudo NMOS. That's an N-type dynamic implementation of same carry look ahead adder circuit. Yes.
So on the previous slide, I'm wondering why we're trying to solve that entire expression for C4 example. For example, by, pulling all of the inputs directly and building all of that logic in additionally, when we could just take C1 and use the output of C1 in the calculation of C2? Or would that just introduce too much delay?
No, that's what we're doing because we want to calculate everything in parallel, right? We want to calculate C1 to C4, everything is parallel. So to calculate C1, we have to perform this logic operation.
Right.
Parallelly, when we are calculating C2, we have to include C1 into C2.
Right.
So calculation of C1 is embedded into C2.
I guess what I'm saying is, would there be a significant increase in delay if instead of trying to just include that
No.
C1 into C2's function?
No, because this equation and this equation is exactly same. At this point, C1 initially is not known. I have to calculate it. Once I calculate C2, because I know what are the dependency of C2, what factor will determine C1, so I can parallelly calculate C2 using this equation. This equation and this equation are exactly same equation. Here, instead of writing C1, I am writing the factors that determine C1.
Right. I know that. What I'm saying is, why are we doing it all in parallel if we could just propagate the
Yeah.
output of the C1 circuit
Okay.
in, would that create too much delay?
So that is basically the whole idea. If I am talking about 64-bit, if we want to do serially, then we could ripple carry adder. So C2 can wait for C1, C3 can wait for C1 and C2, C4 can wait for C1. I want to utilize the factors inside C1 to calculate C2, C3, C4, all in parallel, at the expense of some additional circuitry, because I want to avoid that wait time of the order of n. So yes, you are right. So to implement all this logic function, we are adding a complex array of logic gates, two-step logic gates, just to save time, because that is the most critical, the brain center of the computational center of the computer. So we cannot afford any delay. That's why we want to do parallel. But even in that scheme, as you said, we are making this logic expression unnecessarily complex, and which is evidence from this slide. We are increasing. It is evidence from this slide, because we are adding long series chain of transistor. That's why there is a limit for how large adder you can use carry loop adder principle. But there is no questions that we have to try to do the adder calculation parallelly. We cannot wait for serially C1 to finish its job and plug that into a smaller circuit to calculate C2, and plug that to a smaller circuit to calculate C3, right? So we cannot afford that.
Still end up
that
with the
delay.
same order of n.
Yeah. Ideally, we want to generate all the carry simultaneously. So carry look ahead adder, as I said, so I am showing it also. Mirror technique, the simple one of them is the mirror technique. The series parallel, this is regular CMOS technique for only this one I am showing example. Regular CMOS, series become parallel, parallel becomes series. But mirror technique, you put a mirror over there, right? So there are many different ways to implement this circuit. Regular CMOS, CMOS, N-type dynamic, P-type dynamic, or mirror technique. Now, because carry look ahead adder requires this complex logic circuit to generate all the carry simultaneously, it is not suitable for large array adder. So, people came up with other architecture. One of them is called carry bypass or skip adder. The idea is, instead of trying to use those intermediate signals to generate all the 64-bit or 128-bit carries simultaneously, that makes those carry generation circuits so complex, can we divide that 64-bit adder into smaller block of 4 or 8 and then look at the propagate signal of only those 4? If we know that if the propagates of this one, and this one, and this one, all 4 propagates are 1, without even thinking anything, we can send this carry in to this carry out, right? And then it can go serially. So what we are saying that we are utilizing combination of ripple carry and carry loop ahead adder. If we want to implement everything in ripple carry, then I have to wait for 64 adder to finish its job before I get the final carry. If I want to generate all 64 carries using carry look ahead principle, by the time I reach out to 6th or 7th bit, the logic circuit becomes so complex that it may actually overshadow the benefit you get out of reducing the or eliminating the ripple of the carry. So how can you utilize the advantage of both? That break them into smaller block. Inside the block, it will have 2 options: ripple through 4 adder, or if all 4 propagates are 1, it will bypass that block so that next block can start its operation. If the next block, the propagates are different, it will act like a ripple. If all 4 propagates are 1, it will bypass. So in a 64-bit adder, you will divide them into, let's say, 16 blocks of 4. Statistically, at least you will find that half of them will bypass, half of them will ripple through 4 individual adder. So we are trying to utilize the advantage of both to avoid the disadvantage of both, right? So that is called carry bypass adder, that after every block of adder, we put a mask, multiplexer. If all 4 propagate signals are 1, mux will select this line, that carry in will propagate to the final carry out and it will be sent to the next one. So the next block of 4 will not depend on these 4 to finish their job. So mux will see if all 4 of the 1, it is AND gate, all 4 of them 1 line will be selected, carry in will bypass the block and then it will go to the carry out here, it will go to the next block. If all propagate signals are not 1, this AND gate will be 0, it will select this part, right? So that is called carry bypass. So it's a combination of ripple carry and carry look at adder with the addition of an additional AND gate and multiplexer. The size of the AND gate, the number of inputs of the AND gate will be equal to the block size. If in each block you have 4 adders, that will be a 4-input AND gate. If in the 4-input AND gate, all 4 must be 1 for it to generate a 1, so that it will bypass, right? So this is one way of improving the carry generation delay. Third option, architecture level improvement, is called carry select adder. This one still carry bypass adder. This one still, you don't know, depending on the input combination, you may end up in a situation that no blocks of 4 adder will have all 4 propagates 1. You may end up rippling through entire 64-bit because of that given input combination, plus you will have an additional delay of 16 additional multiplexers sitting in between that line, right? So there is no guarantee that this one will give you delay improvement in all possible input combination or scenario. So how can we do? with the expense of some additional circuit overhead. They are saying that, the next design is saying that we can avoid all those, but we have to spend double the resources. For 64-bit adder, we have to build 102 sets of 64-bit adder. It's called carry select. The carry select is saying that for every column, instead of one full bit adder, let's use two full bit adder. In a 64-bit adder array, in normal design, you would use 64 full adders. But this one is saying that for every column, let's use two full bit adders. One of them, as soon as the inputs are available, one of them will carry out the addition, assuming that the carry in is 1. The other set of column adder will carry out the addition, assuming that carry is 0. But after the previous column finishes its job, in that, so step 1, there will be 2 sets of results generated for every column, utilizing 2 adders available in every column. But after, you know the inputs. After that step 1, by this time, now you know what is actually the carry out from the previous column, because previous column, if they added 1 and 1, you have a carry in. If it is 1 and 0 or 0 and 0 or 0 and 1, there is no carry in. Once you know what is the actual carry in came from the previous column, you pick the result from the 2 available results in each column. So there you have to probably use a mux. If the actual carry from the previous column came as 1, I would select probably left side of the column. If it came as 0, I would probably select the right side, depending on how you place those 2 adders in each column, right? What you're saying? So each column in step 1, you applied the inputs, you know all the input bits, A's and B's. You just do not know what carry the previous column is sending. So you do the calculation assuming that it can be 0, it can be 1. So you do 2 calculations, one assuming carry is equal to 0, one assuming carry equal to 1. 2 sets of result is available after first step. In second step, you exactly know what carry previous column is sending. Use a mux, select the right result, send that right result in step 3 to the output. So in 3 step, you are done. So it's order of 3, no matter it's a 64-bit, 128-bit or 256-bit. In 3 step, order of 3, you are done with the final calculation at the expense of double the circuit resources. So good news is, when you are sending 206-bit bit data, that is a word size of 256 binary bit, you are sending one set of number at a time. So you actually do not need too many arrays of adders in your data path, because they will be adding or processing one pair of word at a time. So that's why, since it is the most important circuit component, it is the important circuit component in CPU, so a redundancy can be tolerated. So in very performance critical design, they implement the adder array with 2 sets of full adder. So with some additional overhead, we get the result at much faster. And there are some different ways of implementing this carry select adder. One is called linear carry select adder, square root carry select adder, but we are not going to go through those advanced design technique at this point. So now if we want to summarize everything we have discussed so far, first we added some logic level manipulation or circuit level manipulation to improve individual full adder or the whole adder architecture. The logic level manipulation will be simple ripple carry adder, that is, and then we did carry look ahead adder, carry bypass or skip adder, carry select adder, and carry save adder. Those are at the logic or architecture level, implementation level, manipulation or improvement to improve certain aspect of adder circuit. Then we can implement inside each of these, each full adder circuit, we can implement standard CMOS using static or dynamic mirror technique, transmission band technique, and there are other some Manchester carry chain, and there are some other special technique, those are hardly used. So these are different circuit implementation for adder circuit. These are some logic and architectural level modification and improvement to improve the adder design. So that actually ends the adder circuit. So in your exam, final exam, I want you to concentrate on slide number 1 to 24 more. There will be maybe small questions from remaining slides, but those mostly conceptual question, but the design question will be from slide number 1 to 24, mainly on adder circuit. So now, let me skip few slides, and then I will, if time permits, I will come back to slide 25. So, two other very important arithmetic operation that will be performed inside your CPU repeatedly. One of them is subtraction, one of this comparison. In binary logic world, in digital calculation, in any digital electronics, addition, subtraction, multiplication, and comparison. These are the four frequent arithmetic operations that will be performed. So, we just finished the adder discussion. Now what? So, you know that in binary algebra, an addition is nothing but a subtraction is nothing but a 2's complement addition. What is a 2's complement addition? If you add a number with the inverted form of another number, the result is actually equivalent to subtraction of number 1 to number 2. Right? So let me explain. A plus B in binary world, sorry, A minus B in binary world is actually equivalent to A plus B bar. It's called 2's complement addition. Subtraction is a 2's complement addition.
Isn't it B bar plus 1? Because that's...
Yeah, 2's complement, sorry, B bar plus 1,
one.
yeah. 2's complement. You have to, yeah. So inside this, you have this 2's complement number. So you send input is a 2's complement adder. You send input directly here, input 2 with an inverter. So the result you get is input minus input 2. So inside this, what do you have? It's an adder circuit. So a subtractor is nothing but an adder with an additional inverter. And comparison or comparator circuit is also very similar. When you are comparing input 1 to input 2, this will produce a 1 if input is greater than input 2. If you are sending input 1 and input 2 like this, input 1 directly, input 2 through an inverter, at the output there is one additional inverter. So the difference, if I ask you to implement a comparator or subtractor, you know how to implement adder. This will be the implementation of subtractor. So the difference between subtractor and adder is, comparator. At the input side same, at the output side there is one additional inverter. So if you know how to implement adder circuit, you already know subtractor circuit, you already know comparator circuit. So that is simple and easy. Now let's look at the multiplier. So multiplication, how we do multiplication. So multiplication, let's say we are show you with the decimal example. 246, we are multiplying by, let's say, 31. Right? The way you do multiplication, first bit of multiplier, this is called multiplicand. I multiply entire multiplicand with first bit of multiplier, the result is 6, 4, 2. Then I multiply the whole multiplicand with the second bit. However, the result I will write aligned with that bit. So it will be left shifted. So this will be empty. So 3 times 6, 18. I have 1. 3 times 4, 12 plus 1, 13. 3 times 2, 6, 7. Right? If I have another number here, 131, then the result of this will be left shifted. The result has to be aligned with this one. 6, 4, 2. Right? And these two will be empty. That's how we do the hand calculation. So, now how do we generate final result? We add column by column. So we add, this is 6, 4 by 6. 8 is 12, we send the carry here, add, we send the carry here, add, we send the carry here, add, then I may get a final carry here, right? That's simple and calculation of multiplication. So binary multiplication, regular binary multiplication is the exact mapping of the way we do hand calculation. So this generation of individual rows of results, which we call it products, are the result of multiplying the multiplicand with each bit of multiplier. And these are known as partial products. Partial products of multiplication. And how do we generate the final result? By adding partial products column by column. So in binary world, when we multiply one binary number with another binary number. Now let's write it in terms of A's and B's. Let's say I have a multiplicand A1, A3, 2, 1, right? So first thing I will do, I will pick B0, multiply entire A with B0. So that means first one will be A0, B0, right? But in the binary world, what is that product? It's an AND operation, right? So each of the rows of partial product is comprised of 1, 2, 3, 4 AND operation, right? If there are 4 multiplicands bit, there will be 4 AND operation. If it's a 6-bit number, there will be 6 AND operation. So the result of those AND operation in successive row will be placed one slot left shifted, right? Aligned with the corresponding multiplier bit, right? So generation of partial products in decimal multiplication, I know exactly what will be 1 times 4, 1 times 2. So from the knowledge of my arithmetics, I put the number. But in binary, this product is AND operation. So the partial products are nothing but series of AND operation. So step 1 in a multiplier circuit is a bunch of AND operation. How many AND operation we are talking about? Let's say if I multiply 101 with 11, this one will multiply these 3. So I need 3 AND operation. 3 AND operation. This one will also, I need 3 plus 3. That means 3 times 2, 6. Number of bits in the multiplicand, number of bits in the multiplier. 3 and 2. If I calculate it with 3 and 3 number, I need 3 times 3. If I need 4 by 2, I need 4 times 2, 8 AND gates. You as the designer, you have to calculate the circuit resources you need. So generate these initial partial products. All you need are 2 input AND gates. These are not complex. Simplest possible AND gates. Each of them will be 2 inputs. You don't need anything more than 2 inputs. So the number of AND gates you need to generate the partial product will be equal to the number of bits in multiplier times the number of bits in multiplicand. That is 0. And then you need what? An array of adders to add those partial products column wise. So this is, I am showing you an actual multiplication, a 6-bit number multiplied by a 4-bit number, right? So in each row I will have 6 products generated by 6 2 inputs NAND gate, and then there will be 4 rows because there are 4 bits in the multiplier. So for this I need 24 and 2 input AND gates. This final result is generated by column wise addition. So to implement a multiplier circuit, what do you need? A bunch of AND gates, which you already know how to implement, and an array of adders to generate the final result. So that's why you see why adder is so important. Multiplier operation, multiplication operation is also implemented using the simplest possible logic gate, one of the 3 basic logic gates, AND or an inverter, AND gate, and an array of adder. Now, if we implement a multiplier using the direct mapping of the hand calculation of multiplication operation, we get the simplest possible multiplier circuit like those ripple carry adder. But that simplest possible multiplier circuit, which is known as array multiplier, it is very inefficient. So all the improvement effort to improve the performance of multiplier circuit is to minimize the number of adder circuit and the delay of carry moving from one adder to another, because we are talking about series of addition every column, right? So here also improving a multiplier circuit is focused on improving the carry generation time from one column to another column, one row to another row. So first look at the first step, partial product generation. All those rows of partial results, those will be, each row will be implemented by this one, right? Let's say X is my multiplier, multiplicand, Y is my multiplier. So every bit of multiplier will be multiplying every bit of multiplicand, right? Depending on how many bits in the multiplicand, you need that many AND gate for that row. If it is Y0, this will be 0th row, Y1, same number of AND gate, but the AND gate connection will be left shifted. Next AND gate row will be left shifted. Every row you will need exactly same number of AND gate. How many rows of AND gates you need? That depends on the number of bits you have in the multiplier Y. So those arrays of AND gates, you cannot put them directly, but physically you put them in a box, but the connection has to be left shifted by one column at a time, right? So that you add them in the right sequence. So based on how we accumulate these partial products and generate the final result using a bunch of adder, based on that approach, we get different types of multiplier circuit. Partial product generation, there is no variation. There is nothing innovative about it. You just need a bunch of 2-input AND gates depending on the number of bits in the multiplier and multiplicand. So there is nothing innovative about it. How do we accumulate those partial product results and generate the final result using a bunch of adder? That's where the difference of efficiency and the design will vary. That's how we get many different types of multiplier circuit. 3 of the most popular types are array multiplier, carry saved multiplier, and tree multiplier. So let's look at their implementation. So here I am showing you an actual example, a 4x4 multiplication, right? So 4x4 multiplication, so as you can see, I have 1, 2, 3, 4 rows of AND gates producing the partial results. 4x4, total 16 partial products, right? So I need 16 2-input AND gates, 4 rows. In each row I have 1, 2, 3, 4. To make it simple, 4. And as you can see, the AND gates are left shifted. Left shifted. Now, in this first 0th column, I don't need any adder because there is only 1 bit. So this can directly come here. So result of the first AND gate, rightmost AND gate at the topmost row, can come directly here. I don't need any adder circuit. Here I need what? To add 2 bits. This one is not sending and carry in here. So a half adder will do. A half adder can take 2 input bits but cannot take any carry in, right? So these 2, I need a half adder. Half adder, the 2 inputs of the half adder, one will come from the top row, one will come from the second row, right? In the next column, I have 1, 2, 3. Then, if there may be a situation, it is 1, it is 1. In that case, first column may generate a carry and send it to the next one. So the next column already has 3. Now it can get a carry from the previous column, so it has to add 4 number. There is no single bit adder to add 4 numbers. Full adder can only add 3. 2 inputs, 1 carry. So if it takes 2 of these inputs from row 1 and row 2 and plus the carry of previous one, then this full adder is fully occupied. The result it is generating must be added to the third one to generate its final result of that column. So I need another half adder, right? So that's how you calculate. And then here, it already has 1, 2, 3, 4 number. It can send another carry. So I need 1, 2, full adder, and then another half adder, because these first 2 may be 1 and 1. It can generate a carry. Together they can generate another carry. It has to be added. It can generate another carry. It has to be added with the last one to generate the final result. So the next column you have 1 full adder, 1 full adder, and half adder. Yes.
Would there be any benefit to adding a multiplexer stage in front of each of those rows, so that if we knew that the input of one was going to be, if the multiplier of one was going to be a 0, that we could just automatically propagate?
At this point, you will not get, because then you need like multipliers at the input of everyone. So it will only increase the circuit overhead. But this one is not the efficient design. We will see. So, but this one is exact mapping of the way the hand calculation is done. It is called array multiplier. So the problem with this one is a signal can start from here. It can go down here. It can go propagate this way, or it can go propagate this way, or it can propagate this way. This come here, or from here it can go this way, this way. So from the first bit to the last bit, there are many paths of equal length through which signal can propagate. So in any circuit design, we always try to identify the longest possible path from the initial input to the final output. And we attack that path, try to improve the delay of that path to reduce the worst case delay. But in array multiplier, there is no way I can identify a worst case path. If I start from here, I can go this way, I can go this way. The number of adder and AND gate the signal must hop on will be exactly same in 5 different paths from beginning to end. So there is no longest or critical path in this multiplier. So I will just end with one more slide. So this is a very simple design, exact mapping of the hand calculation, but it is a very inefficient design because there is no longest path, there is no shortest path. So there are many different critical paths showing the blue, red and green. So the overall delay will be given by this. That in each path it has to follow multiple number of adders and AND gates. This is the delay. So what can we do? A simple improvement can significantly improve this array. So now let's go back to this one. The carry generated by this column must be added with this column. Does it really matter if I put it on the top or at the bottom? No. As long as I am adding these three numbers with the carry of the previous column, I will get the correct result. In the direct hand calculation, I send it horizontally with this one in this group, add it and then add it and then add it, right? That's why you see I am sending carry of this column horizontally to the next adder. But as long as I send this carry to this column anywhere, add it here or here, same result. So utilizing that possibility, a simple tweaking of the adder design leads to this one. Carry out of this is connected diagonally down to this one. This one's diagonally connected to this one, diagonally connected to this one. So now for this signal, initial signal, it has only one possible path to travel. So now I have only one critical longest path. All other paths will be much shorter. So 1, 2, 3, 4, 5, 6, 7 adder in this path. But in the previous design, there can be 7 different possibilities. Each one will have 7 adder, right? So there is no way to optimize. But here, I can focus on this particular path and use extremely high efficiency adder only for this path and improve the overall delay. I don't care about other paths because those are much shorter path. So that is called KD save multiplier, that instead of sending the KD immediately horizontally to the next bit, save it, for that two to finish their job, send it downward to the lower number of bit in the same column. That way, the adder, the multiplier can be very, very efficient. With that, there is another one called tree multiplier, but that is a trial and error basis. Tree multiplier hardly utilized in any design. So we are not going to explore that. So for your final, stay until slide number 30 and go down to last one. So basically I am skipping 2 or 3 slides. Those are just elaboration of multiplying. So, as I said at the beginning of the class, the TA already uploaded 2 quizzes on the Canvas. You have to log in using your UMKC ID. Once you start the quiz, you have to finish it within 30 or 35 designated minutes. You cannot log out and go back and then do it second time. So you have to take it in one sitting. So right now,
There's only one try.
yeah, one try. You have to, right now, you have to, I think, finish it by tomorrow midnight, but I will ask him to
Change it to weekend.
Sunday midnight. So during the weekend, you can take the quiz anytime.
Yeah.
So, and then, during the weekend, he will also email you an extra credit assignment based on lecture 6 to 10. This extra credit assignment is for anybody who wants to improve their grade. So if you are already in the overall, the current, if you are already above the A card, then you don't have to worry. But if somebody is in the borderline and wants to improve their grade, so we are going to use it as a bonus mark, it's extra credit assignment. Okay? Thank you. It has been a very, very challenging semester for me, simply because every day I need 24 more hours.